Hello, I am Stephen Wheat. I am a Senior Director for the HPC Business Group at Quanta Cloud Technologies. Today we will be reviewing the vision and progress towards an adaptive platform for converged HPC and AI workloads. The motivation here is that HPC and AI-based computing interests have intersected each other. Existing solutions are inadequate for the challenges of sufficiently supporting each community. There is the need for a software-defined environment that seamlessly supports traditional compute-oriented HPC workloads and the emerging artificial intelligence workloads. QCT sees opportunities in improving HPC and AI workload performance, development, and deployment with emerging technologies, including heterogeneous computing, software-defined storage, and containerization. We understand the difficulties of creating, managing, and maintaining the workload environments for HPC and AI applications. We have developed a workload-driven approach to design our HPC and AI system solutions. In so doing, we have created a platform that supports quick deployment that is easily managed and provides proven optimization of HPC and AI workloads. We will share our experiences in optimizing the HPC and AI workloads and how we address them with the state-of-the-art hardware and software solutions. On the one hand, we have high-performance computing that uses substantial computing power with parallel processing techniques for solving complex and advanced problems and performing research activities through computer modeling, simulation, and analysis. On the other hand, we have the various AI domains that use algorithms and techniques that iteratively learn from data to allow computers to find hidden insights without being explicitly programmed where to look. In fact, fast-growing data sets and the increase in computing power at affordable costs are driving the convergence of HPC and AI. At QCT, we do not just build a generic platform. We work on users' workloads and build optimized HPC and AI solutions for those workloads. HPC design should start with the workload, not the hardware and software infrastructure. The workload-driven approach is a cyclic process that we can give you a head start on pursuing. Let's have a look at what we mean by workload and how various workload differences drive the demand for distinctly optimized solutions built with common building blocks. Here we will use statistics from the NERSC workload to show you the typical HPC workloads. Here we display the three focus performance metrics that provide the basis for workload-specific optimizations. We focus on the application needs for the three most common sources of performance bottlenecks: CPU throughput, or flops, memory and network bandwidth, including I/O, and network latency. For example, workloads for astrophysics, chemistry, and material science, which involve algorithms using dense linear algebra and structured grids, require high floating point operations for the processors like CPUs and GPUs. Workloads for astrophysics, chemistry, climate, and lattice gauge, which use spectral methods for computation, require high memory bandwidth and high network bisection bandwidth. And most of these also have large input and/or output data sets, so the I/O bandwidth is also important. And the communication latency between processors and nodes are often neglected. For example, astrophysics and climate workloads, which have a lot of exchange on the unstructured grid, are sensitive to communication latency. To best design a platform for converged workloads, we need to understand the characteristics of real-world applications in different domains. For example, key EDA applications rely on double precision-based computing power and a parallel file system with high file throughput. In contrast, single precision or even half precision is used for deep learning. As depicted in the table, each application domain has its own characteristics with a different mix of compute-bound, memory-bound, or I/O-bound. After understanding the workload profile, we should know the strengths and weaknesses of each technology and how they support specific workloads. The CPU has the most flexibility for general-purpose workloads. The ASIC is optimized for specific workloads. The GPU performs well for HPC and deep learning workloads. The FPGA has a reasonable balance of cost, efficiency, and flexibility. There is no single technology that can fulfill all requests and preferences in a cost-effective manner for all workloads. As with the myriad computational workload metrics, storage subsystems have different metrics for performance, most notably performance, capacity, and persistence. Understanding the data profile and workload demands leads to the best fit storage type and technologies. File systems would be for structured hot and cold data storage, and they provide an easier way for user access, but generally have higher costs. Block storage performs the best, but with limited scale, and they usually need NVMe drives to support high performance. Object storage is the cost-effective way for the unstructured cold data storage with high scalability. As for the network, there are also different metrics and technologies to support the diverse demands. The very common fat tree topology is widely employed in clusters to support high bandwidth and low latency interprocess communication. A multi-dimensional torus, on the other hand, is optimized for nearest neighbor interprocess communication. And finally, for large-scale deployments, a dragonfly is a fully connected topology which suitably supports substantial large systems, including exascale size. On the software side, there are different ways to distribute workload to the processing unit, like CPU, GPU, and FPGAs. OpenMP uses shared memory within a node. MPI uses distributed memory across nodes, and there is also the hybrid method, which combines both of them. For MPI, the pros are that it's portable to distributed and shared memory machines. It scales beyond one node, and there's no data placement problem. The cons are that it's difficult to develop and debug. It has high latency and low bandwidth as compared to shared memory actions. Explicit communication for the programmer, has large granularity, and it's difficult to support load balancing. For OpenMP, the pros are that it's easy to implement parallelism. It has low latency, high bandwidth, implicit communication, coarse and fine granularity, and supports dynamic load balancing. On the cons, it only is supported on shared memory machines. It scales only within the node, and it's possible to have data placement problems. No specific thread order is imposed either. Let's now take a look at the workload optimization process. Workload optimization is a continuous effort. First, we design the benchmark to evaluate the performance of the workload. Then we measure and evaluate its baseline performance. Furthermore, we profile the workload to find the bottlenecks in the current configuration and settings. And we can start from that to improve our configurations of the hardware and software and the workload itself. After that, we evaluate the performance of our new configuration. From there, we go through the process again to improve further with the profiling to find out the new performance bottleneck or bottlenecks. Perhaps this is what any user would strive to do. But once done by QCT, the end users need not do it, or they can start with this as an optimized solution and continue to seek further improvements for their particular data sets. These are the things to consider when we try to optimize a workload. Single node to multi-node scaling, multi-core to many-core scaling, heterogeneous computation between CPU, GPU, and FPGA, interconnections between nodes, considering bandwidth and latency, discerning whether it's CPU intensive, memory intensive, or IO intensive, data patterns and workflows, combinations of libraries and compilers, compiling options, interconnection options and settings, and workload component resources allocation. And there is no one solution that fits all. Here we will step through the process done by QCT for the WRF or WRF workload. As you may know, WRF is a popular weather modeling software package that occupies a significant portion of HPC use worldwide. We use WRF here as an example for workload optimization. We utilized the methods mentioned before and found out 4 major factors that impact the WRF performance. First is the Fortran compiler. By far, we found the Intel Fortran compiler still outperforms other compilers in the Fortran applications. In our case, the Intel Fortran compiler outperforms the competitor by as much as 25% for WRF. With the fabric, we find at times that the performance differences between MPI libraries can make a significant difference. However, in this case for WRF, OpenMPI and mVapage2 are pretty close to being the same, with mVapage2 coming slightly ahead. The Intel MPI is right there with both of them. However, as the node configuration changes by CPU model or memory configuration or fabric configuration, we'll find differences that would be more substantial, and that particular library that is favored in that situation would be pre-configured for that solution. One interesting feature of WRF workload is its performance dependency on communication latencies. Remember that OpenMP allows processor cores in a single node to share the same pool of memory. In this case, when the OpenMP task is divided by 8 threads per task on our 20-core CPUs, we find that because 20 is not divisible by 8, one of the task sets must be split across the 2 CPUs, and that increases the communication latency between the cores for that task set. That increase of latency could result in a performance loss of as much as 25%. Consequently, the configuration files would avoid thread sets that don't fit well on the chosen CPUs. And we find that I/O can have a significant impact as well. We exploited a BGFS parallel file system feature. We enabled parallel write capability of WRF and let it output split files. Here the output time is decreased by a factor of 20. In this brief journey example, we found that the optimized hardware stack with high flops rate and low latency, optimized software stack with compiler and dependent libraries, and optimized setting for a WRF workload to unleash the potential of the hardware and software stack with the lowest latency path and parallel I/O demonstrates significant enhancements. The next step would be to go through this again and look at additional bottlenecks. We have generalized the overall workflow optimization process to develop workload-specific platforms. The overall platform framework is called QCT POD, which stands for QCT Platform on Demand. Today, customers are increasingly seeking best practices systems which meet specific workload demands. So a workload-driven business becomes more important than ever. However, to build an integrated workload-driven system with optimized performance costs lots of time and resources. As we saw with the WRF example, it takes several stages from the initial planning to the final readiness for users, which are demand pattern analysis, system design and architecting, system development and deployment, system tuning and performance benchmarking, piloting, and then finally turning it over for general use. In order to accelerate time to value and enhance the efficiency, QCT is developing pre-validated and pre-configured system concepts to provide pre-configured system solutions to the customer. Again, we call this QCT POD. QCT POD stands for, again, QCT Platform on Demand. It is a concept of an on-premises workload-driven design integrated system. Under this concept, QCT will provide various solutions with best practice combination of hardware and software integrated for specific workloads. The QCT POD platform includes diverse common building blocks which have greater flexibility and scalability to meet different customer demands. It also includes management tools to simplify the deployment and management process. With the pre-validated and pre-configured rack-level system designs, QCT POD solutions also offer suitable power and network cabling to rapidly deploy the system at the customer site. A QCT POD solution can be developed in a converged or a disaggregated structure. In the converged system, all the functional building blocks like management, compute, storage, and networking will be delivered in one rack. While for the disaggregated system, various building blocks will be separated in different racks. To best fulfill the workload requirements, it is important to understand the attribute of each building block in a QCT pod. For example, we have big memory, accelerated and high density feature building blocks for the compute. We also have IOPS optimized, throughput optimized, and capacity optimized building blocks for storage. According to these attributes, we configure a given pod to the customer's workload demands. To be more specific, let's look at the general architecture and configuration of a QCT pod system. We deliver QCT pod with management, compute, and storage building blocks, and each of them is connected by the network fabric. It includes diverse technology components. From the bottom, QCT pod is delivered with our best-in-class hardware system. As for the software stacks, it includes open source software recommended by QCT and certain pre-validated and commercial software. With various components and building blocks, QCT pod has the flexibility to modify the architecture by workloads. The structure of compute and storage building blocks can be much different between the workloads. For some customer workloads, some building blocks may not be necessary. However, the dashboard-based management building blocks will always be necessary to provide for simple system management and monitoring. In the QCT pod system, no one can directly access the compute and storage building blocks. All the control and management is done through the management building block. For the users and developers, QCT pod includes user interfaces, development tools, and pre-compiled workload packages to simplify the operation and accelerate the time to put the system into service. With a comprehensive development platform, developers can focus on their specific development and leave the QCT pod to deliver the framework. It is always a big challenge for administrators to deploy and manage a cluster with hybrid infrastructure and diverse services. With QCT pod, administrators can deploy the operating system with configuration management via XCAT and Ansible. The modern web-based dashboards, log alerting systems, and useful administration tools such as Prometheus, Grafana, ElkStack, and WebMin are also pre-built into the system. Additionally, there are internal core services such as RMS and Kubernetes supporting the in-management building block. As mentioned before, QCT has a comprehensive portfolio of best practices, leadership class, system building blocks to support myriad distinct usage demands for the high-performance computing and AI environments. Pause here to briefly review these solutions. For storage, QCT utilizes its relationships with third parties to bring greater value to the customer. File storage, here we have BGFS, Gluster, Lustre, and more. On block storage, we have Accelero, object storage, NetApp, Ceph, and more. As with the WRF solution, QCT pod solutions have also been developed for these workloads: intelligent video analytics and multi-object detection. In this talk, I have reviewed QCT's Adaptive Platform, QCT POD, along with its benefits. First, QCT POD can deliver excellent workload performance with a flexible building block design and a pre-configured workload environment based on QCT's outstanding engineering domain know-how. Second, QCT POD system simplifies the management with the administration dashboard and speed up of deployment process with suitable power and network cabling. Third, QCT could accelerate time to value for customers through the pre-validated, pre-configured QCT POD system building blocks. QCT has various end-to-end platform solutions and services based on cutting-edge technologies for different application workloads. We anticipate developing additional QCT pod-oriented solutions for many of these vertical use cases shown here. Please feel free to contact us for any questions and interests you may have. Thank you for taking the time to review our adaptive QCT pod platform solution concept. We look forward to seeing you in the marketplace to fulfill your computational and storage needs. This concludes the presentation.